everyone. Welcome back to SAT Math Question of the Day. Here's our question of the day. Please read it, pause the video, come back, and we'll do it here. M of t is 10 times 1/2 to the power of t divided by 7530. The given function m models the mass of the radioactive isotope carbon-14 in a sample in picograms t years after the initial measurement. How much time in years does it take, for the, sorry about that. How much time does it take for the mass of the carbon-14 in the sample to decrease to 5 picograms? Oh, okay. How much time in years does it take for the mass of carbon-14 in the sample to decrease to 5 picograms? So in other words, we want 5 to be here, and we have 10, 1/2 to the t divided by 7530. So it's an equation. One equation, one unknown. So 5, do we want to isolate this whole thing? So we divide by 10, so we get 5 over 10, which is a half. Oh, wow, is equal to half of t. Wow, this is solving pretty easily, because this half is 1/2 to the first power. So, after seeing this, you could realize there's a massive pattern in this, and the answer is 7530 years. And talk about patterns, that if you just understood what half-life was and what this means, you could immediately say that, if it goes from 10 to 5, it goes half of that. So of course it's one set of 5730 years. So the answer is one set of 5730 years. Now we have to go back and translate that into what they want. One set of 5730 years. How many times in years? So the answer has to be 5730 years in order for this equation to be satisfied. 1 is equal to t divided by 5730. T in years is 5730. So, doing it the straight arrow way and not even realizing that, this is just half, would take 30 seconds, 20 seconds to do? If you realize, so you do realize immediately the answer is 5730 in 3 or 4, 5 or 6 seconds?
Well, yes, you could just look as, observing that the function is 10 times this exponential. The exponential needs to be 1/2 when the mass goes down to 5, and the exponential becomes a half when the exponent is 1, and the exponent is 1 when the numerator equals the denominator. The denominator is 5,730. So the answer is 5,730.
Yeah. So there is as part of one of the questions we asked, there is a serious pattern to this question. In that they're just saying how much does the thing go down by how long does it take for the sample for its mass to be divided by 2 or cut down by half or multiplied by a half, and it's one of the half-lives, and the half-life is 5730 years.
Well, the pattern is that when for exponential decays of things, one popular way of quantifying them in science is by what's called half-life.
Yeah.
And the half-life is the time it takes for the thing to decay to become half of what it was. And the pattern for half-life, in exponential decay is 1/2. It's called the initial value times 1/2 raised to the time divided by, and in the numerator is the half-life.
Right.
And the cool thing about it is that when t equals the half-life, then the exponent t over equals 1. 1/2 to the 1 equals 1/2, and m is equal to the initial times 1/2. So
Yep.
the pattern, this is the pattern. When you want half-lives, the coefficient is the initial amount, the exponent is 1/2, and the base is 1/2.
The base is 1/2.
And then the exponent is scaled by the half-life in the denominator.
Exactly.
That's how you do half-life.
The exponent is the number of half-life.
Half-life. The exponent is the amount of time for when the exponential factor equals 1/2.
Yeah. Right. Yeah.
The exponential factor has base 1/2, and so the factor equals 1/2 when the exponent is 1.
Yeah.
Because the base raised to the 1th power equals the base.
Yeah. I mean, I also think of it as this exponent here is the number of half-life periods. So one period is 5730. You go 5730 years, the thing gets cut by 1/2. You go another 5730 years, it gets cut by 1/2. You go 5730 periods, it gets cut by another 1/2. So it ends up as an 1/8 because it's 1/2 times 1/2 times 1/2. It gets an 1/8. So this is really the number of periods.
Three times the half-life. If you plug in t equals 3 times half-life, then the divide that by half-life, and you get 3.
Okay, that's right. Yeah, because it's the number of.
And the amount of decay is 1/2 raised to the 3rd power.
Right.
Which is 1/2
right.
of 1/2 of 1/2.
So what are we really doing? Why do we just keep regurgitating this? We keep regurgitating this because it's important when you learn equations to really understand them, as opposed to just memorize them. You really understand what's going on. Like, why does this have such a weird look to it? That's just a strange thing. But if you think about what it means, then 1, you get a much better understanding, and 2, there's more of a chance you're going to remember it. And more of a chance you're going to apply it correctly. So that's why we spend this time regurgitating things that, we really don't need to regurgitate. So let's get to our questions. Patterns, yes. Oh God, there's a super pattern here. If you just realize that 5/10 is 1/2, then you immediately say, boom, oh, that's 1/2 life, 5730, problem done. You got the pattern there, and you save yourself 30, maybe 20 seconds, 25 seconds. So you don't actually have to do the whole equation. Calculator, no, actually, calculator really doesn't help. I mean, really, 5/10, most people hopefully know that that's 1/2. This is a calculated question, but all the SAT questions are now calculated questions. Start with the answer. No, you can't do that. This is free response. How would you do this different from school? That'd be the same, except it probably would be a little harder. A harder question. And the main idea. So, what are they? In some ways, because they give you the equation, you don't really even have to understand anything other than solving an exponential equation, or solving an equation where there's an exponent in the as the unknown. So you don't really have to even understand half-life. You just solve the equation. So it's exponential equation solving is a skill that would they may be testing. I guess also sort of understanding a word problem, but they give you the equation. There's no equation to write. Uh, I guess, yeah. I mean, it's just, I guess, reading the problem and trying to understand what you need to solve for. So, yeah, that's good. That's a skill. Just reading a word problem, giving the equation, understanding what you need to do. So, what do you think? What other skills do you think as a test taker? As a test maker. As a test maker, I always say that. As a test maker committee, what do you think the goal of the committee members were in this problem? Seth, are you there?
Well, not get understanding enough about science to uh, not get thoroughly confused by the question.
But if you just cut away all the words,
Yeah,
if you
yeah.
just cut
No,
away all the words,
I would think that people who had no idea what's the subject of why you learn stuff in school? What are all the things? There lots of technical words
yeah,
in this. It's in all sorts of questions. What function,
yeah,
mass, radioactive, isotope, carbon. Maybe what's a sample?
yeah,
What's a sample? Yeah.
yeah,
In what's this picograms?
yeah, right, yeah,
Ah, what? Of course, maybe commons was years. Most people, people would learn about years outside of school, but using a letter for a number. That's something I remember being was new when they taught it in school.
yep,
Measurement. What are measurements?
yep,
Time. Time in years may be common. It take for the mass again. Mass. They use what's this mass thing? What does mass mean? Again, they said carbon,
yep,
and then decrease. Well, decrease, but how do you deal with decreasing mathematically? And then, of course, arithmetic.
yeah,
There's 5 here, and then another thing that you must know how to interpret is this is function. It's a concept, and then there's this formula. There's this all these symbols mushed up together. What does all that mean?
yeah, yeah. So that's not that.
There's a
That
lot.
is,
So there's a lot of stuff that goes into education.
yeah. So there's a lot of things they're trying to see whether you know how
Yeah.
to
So
do.
the tests. It tests how educated you are, ready for college.
Yeah, yeah, yeah. Yeah. Um, Yep, and I guess they don't necessarily tell you what the 10 means in the problem. They don't really tell you actually what any of the numbers mean.
No, well, a broad understanding that comes later in learning all the science is that, see, it tells you the function models the mass.
Yeah.
So the kinds of units, the units for the values of m are units of mass, and the coefficient is multiplied by a fraction raised to an exponential power. And so the fractional things with a varying exponent has no units. It's a fractional number. It's a number
Yeah.
without units.
Yeah.
And so the coefficient must have units of mass.
Of course. Right. So it must be
And
that
then
10.
when at the what do they call it? At the time of the initial measurement is when t equals 0.
Yeah.
T years after the initial measurement. Well,
Yeah.
at the initial measurement, it's 0 years.
Right.
Right? So at the time of the initial measurement, t equals 0.
Yep.
The rule of exponents, the exponential of 0, any base raised to the 0th power is 1.
Right.
Right?
Yep. Yeah, that's
and so the initial mass is the mass when t equals 0, which is 10 times 1.
Yep.
So all that whole constellation of understanding stuff is the subject of this question.
Right. Yeah. 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 I noticed that they say after the initial measurement. No one was there. We don't know. 55,730 years ago. Nobody was there measuring the initial mass of the carbon-14. But the dinosaur, whoever
you
was
don't have
alive.
to wait. So you could, in the laboratory, they can measure half-lives without waiting for the whole half-life to.
Oh, that's true. That's true.
You measure how much it decreases.
That's true.
And as soon as you can measure how much it decreases, you could do calculations.
Right. That's right.
Like, suppose it decreases. If it decreases by, suppose m of t, m of you test it for a year.
Right.
1 year.
Yeah.
M of 1 year, say, equals 9.8.
Right.
You want to find the half-life. So you write 9.8 equals 10 times a half raised to, well, the 1 is t. So it's 1 over the unknown half-life.
Right. Yeah.
You want to find out what the half-life is.
Right.
Right? So you could solve for this.
Right.
You have to divide, so you say 9.8.98 equals a half times a half raised to the x power.
Right.
And a calculator can solve for x.
Yep.
And then you write x, you find x equals 1 over half-life, and therefore half-life is equal to whatever you find x to be, you calculate.
Right.
1 over it and tells you the half-life.
Right. You don't have to wait 5,730 years.
Yeah.
Okay. So
so it's not long after the discovery of radioactivity, scientists measured half-lives of all sorts of radioactive substances.
Yeah.
Now, the amount, how do they measure the amount of the radioactive isotope in a sample? They don't measure it by weighing it. They measure it by the average rate of radiation.
Yeah. Right.
They can measure the intensity of the radiation.
Yeah. Right.
So what they do is, instead of measuring the mass, they measure how the intensity of the radiation diminishes as time goes by.
Okay. Right. I mean, that's proportional to the mass.
And that's proportional to the mass. The mass is the amount is proportional to the number of atoms.
Yeah.
Of the radioactive isotope.
Got it.
Right.
Yep. So
radioactivity is really handy for measuring determining very, very, very tiny quantities of substances.
Yeah, as long as they're radioactive.
as long as they're radioactive.
They're radioactive.
Well, and so what they do is they'll take a substance or they'll build a version of the substance with a radioactive isotope for one of its atoms, and then they'll use that substance in an experiment, and then they use the radioactivity to tell how much of that substance is in the sample after they've done an experiment. This is done awfully a lot in especially biological research.
Oh. Yeah. Okay, this is good. This is giving us a little bit of literally fleshing out the problem with the biology research. Okay, so I think we're done, right?
Right.
I'll close with our introductions, like we always do. I'm Joel. I have a PhD in mechanical engineering. My brother Seth has a PhD in math. He's been teaching computer science at State University of New York in Albany for many years. He's now retired. We are here. We try to meet every weekday to go over an SAT math question and to give insights and methods and share our thoughts as to how to approach it, how to think about it. We look for patterns. We just try to give advice on how to do these problems. In terms of studying for the math SAT, please go to the College Board and take as many of the practice tests as you can. They have 4 digital tests. You should take all 4. Look at what you're not sure about, what you don't know. Go to the Khan Academy, a digital SAT course, because they partner with the College Board, and on that course they have all the topics and 10 or 20, 30 questions per topic to give you practice on any topic you're weak on, and look out for stupid mistakes or look out for little traps. Be cognizant of those and practice, and most importantly, learn from your mistakes and learn whatever material is on the test. That's about it. Please dislike our videos. We take all our comments very seriously. We read them all. We respond to them all. And if you have any SAT math questions that you'd like us to go over, please email them to us at satmathquestionoftheday@gmail.com. I guess that's it, right? And tomorrow's Throwback Thursday. Right. So we're going to go take one question from a test from about 20 years ago and discuss and look at it. And you'll see that some of the questions from 20 years ago had a whole different feel to the modern questions. Okay, everyone. Have a great day.
Bye.